Hi everyone. We're going to begin the topic of experimental error now. And once we talk about experimental error, we're going to be using words like accuracy and precision. And since the number of significant figures in a measurement reflects its precision, let's begin by reviewing the rules for significant figures in arithmetic. I know you're familiar with the rules for addition and subtraction and multiplication and division, but you may not be that familiar with the rules for logs and antilogs. So that's what we'll focus on now. About the sig fig rules when taking a log and an antilog, and this is going to be important when we do pH calculations. So let's remind ourselves what a log means. So let's recall that when we have the log of n, which is equal to, let's say, a, that means that a is the exponent. 10 to the power of a equals n. And there's something special that we can say about this value a. It has a so-called characteristic and mantissa. So the value a has what we call a characteristic and a mantissa. And these may be new vocabulary words for you. So let me define what characteristic and mantissa mean. If we have the log of, let's say, 339, you'll find that that's equal to 2.530. So again, this is n and this is a. The value a has a so-called characteristic. The characteristic is everything to the left of the decimal place, and the mantissa is everything to the right of the decimal place. So 2 would be the characteristic of A, 530 would be the mantissa of A. So looking at this example, are you able to deduce the rule for sig figs when taking a log and an antilog? I'll give you a minute to think about that. Did you deduce the rule? Here it is. The number of sig figs in n, which is 3 here, is equal to the number of digits in the mantissa of a, which is also 3. So let me write that down. The number of sig figs in n is equal to the number of digits in the mantissa of a. The number of sig figs in n, that's 3, is equal to the number of digits in the mantissa of a, that's also 3. Let's see if we can do some examples now. So why don't we try this first example, the log of 5.38. Again, that's n. So when I do this arithmetic on my calculator, I get 0.7307822276. So again, 5.38 is n, this is a. The number of sig figs in n, that's 3 sig figs, equals the number of digits in the mantissa of a. I need 3 digits, so I could call this 0.731. Or I could also write it as 0.73, maybe with an insignificant 8. It just depends on if you were going to use this value in a subsequent calculation. Let's try this next one. 1.2 times 10 to the 12th, when we take the log of that, I get 12.079182125. So again, this is n, this is a. I have 2 sig figs in N, so I need 2 digits in the mantissa of A, so I could call this 12.08, or if I wanted to, I could call it 12.07 with an insignificant 9. Let's try this one where we're actually taking the antilog of a number. So now A is the exponent. So let me take the antilog of 4.29, and when I do that, I get quite a large number. I get 19,498.446. And again, this is N. So let's follow the rule. We have 2 digits in the mantissa of A, so we only need 2 sig figs in N. I might want to convert this into scientific notation to be really clear about the sig figs. I only need 2. I would call that 1.9 times 10 to the 4th, or if I wanted to, I could call it 1.9 with an insignificant 5 times 10 to the 4th. And let's do this very last one where again we're taking the antilog. So again, 5.1 is A. When we take the antilog, we get 1.2588925 times 10 to the 5th. And again, this is N. So what is our rule? We've got 1 digit in the mantissa of A, so we can only have 1 sig fig in our answer. So I would call this 1 times 10 to the 5th. Or if you needed to keep a few digits, I would say 1 point with an insignificant 3 times 10 to the 5th. So hope you enjoyed maybe learning this new rule on using sig figs for logs and antilogs. Thanks for listening.